approximation using the derivatives. Now you will remember when we started derivatives, we were looking at a sketch like this, and we said that if I want to find the gradient between 2 points, let this be x, then the y value will be the function at x, and if this distance here is h, then this will be x plus h. And if my x value is x plus h, where it intercepts there will be f at x plus h. And I said then that the gradient at any point equals the change in y, so y2 minus y1 over x2 minus x1. We said that. Right, and from there we said then, well, y2 is fx plus h, and what we got then is x plus h minus fx divided by x plus h, my x2 value, take away x. And that was our gradient between the two lines. And that gives us h. So that was the gradient of this green line. What we then said is, but we don't want the gradient just between two lines. We want the instantaneous rate of change. We want to find what is the gradient at a specific point. So what we did is we made this h smaller and smaller and smaller until it just touched the line, until it was just touching that point. Then h was 0, which gave us a problem because h cannot be 0 because I'm not allowed to divide by 0. So one of the methods what we did was we made h very, very small. When we made h very small, we said as h approached 0, what does my function, what does this gradient then approach? And from that we said, remember we said approach, so as the limit, we limited, so we said that the gradient equals the limit where h strives to 0 of fx plus h minus fx over h. And we said that that m, this gradient at a specific point, is called my derivative. So the derivative of fx equals the limit where h strives to 0 of fx plus h minus fx divided by h. So that will still give us the point at there. And this is an equal sign. It is exactly equal to, and we proved it that way. What we're going to do now is we're going to look at approximation. We said, okay, let's say it's not exactly there. Let's say h is a very, very small number. If h is a very, very small number, then as we've done previously, it's going to change my equation. It will then become the derivative of x. If h is not 0, we're not going to calculate the limit. We're going to go back to this fx plus h minus fx over h. But that's all going to be equal to, it's going to be approximate, because it's going to be much closer. It's not going to be exactly, but it's going to be very close. And this is then how we're going to find the approximation. We're going to say for a very small value of f for x, for a very small value for h, this is what's going to be true. Now if I rearrange this, I'm going to multiply by h on both sides. I'm going to get h times the derivative, f derivative of x is going to be equal to fx plus h minus fx. So all I did was I multiplied by h on both sides. What I'm then going to do is I'm going to bring this to its own side. So I'm going to take negative fx to the other side. It becomes plus fx, and I'm going to swap the two sides. So I'm going to swap the two sides. It becomes fx plus h. And I'm going to bring this over. It becomes positive. So it's h derivative of fx plus fx. Okay. Now I'm going to just swap this to it. I'm going to say this is then for some value of x. for some value of x, and we're going to call that some value of x. Let's just write it in another color over here, because this is the formula that you have to remember. So for some value, and we just call it x0 for the one that I choose, I'm just going to change all the x to x0. So it becomes f at x0 plus h will be approximately h derivative of fx0 plus f at 0. And that is the formula that you have to remember if we ask you to find approximation using derivatives.